Hello and welcome back, heavyweight champions of Leetcode. We're looking at a problem which is medium, but in my opinion, it's not that medium. I found it a little harder. It's delete node in a binary search tree. So we're given the root of a binary search tree, and we're giving an integer key, and we wanna find first if that node exists in our binary search tree, and if it does exist, and then delete it. So basically the deletion can be divided in two stages: search for a node, and if node is found, delete the node. And then what we have to return is the root of our updated or not updated binary search tree. So in this case, if we're looking at the first example, if we have to delete this tree right here, we could up 4 and have 4 and 2, or we could just put 4 here and 2 could be on the right side of the root. So let's jump into our whiteboard and see how we can solve this problem and what are the steps, what we have to think about it when we're trying to even attempt this problem. As I said, it sounds easy, but for me personally, it wasn't that easy. So we know we have two steps, right? We have step number 1, find the node, right? That's what we have to do, the first thing, right? If we don't find the node, if they give us node 100 and node 100 is not here, we'll just return the root, right? So that's step number 1. Now, step number 2 is we found the node. Let's say the node is this one right here, node number 1. And they want us to delete this node number 1. So how are we going to delete this node? By looking at this node, it's pretty simple to see that this node is a leaf, right? That it doesn't have any children, right? There's no children. So if we made it to a node that is a leaf, and that's what they asked us to delete, we could just initialize this node to null. So basically this is going to point to null. So this node is not existing anymore, and we're just returning our root, what they gave us at the beginning. So we could say that step A from step 2 is if our node is leaf, if leaf, just make it null, right? Make it null. Right. So that's step A. Now, what could be a different scenario? We could have one node like this node right here. And this node, we can see that it's not a leaf, but also it doesn't have two children. So how would we delete this node right here? We could see that all we have to do is get the parent, which is 2, and just link it to the children right here, right? Just link it to the children, and then this 4, it will be right here, and then here will be nothing. So that's it if our node has only one children. So step B, we could say if one child, just remove it, or like link parent to children. Then we're stepping into our third and last step, which is also, I think, here's what I had troubles with. I found it like most challenging to understand. So let's say they asked us to remove this node right here. They asked us to remove node number 8. How are we going to do that? Because if we're removing node number 8 right here, we can just bump the 6 in here because we're losing everything that's here, and vice versa, we can just put 9 in here because we're losing everything that's in here. So how are we going to do that? And as I said, I had most challenges with this part. So we know, since this is a binary search tree, we know that everything in the left of here, it's smaller than my root, and everything on the right is greater than my root, right? So all we have to do now is find our maximum in our left subtree. So find the maximum value that's up here. And the maximum value in this case is 7. And now once we found that maximum, we're just going to swap, or we're just going to replace this root value with our 7, with the maximum. So this will become 7. So this is no more 8, but it becomes 7 right now. And then all we have to do is delete this 7. So is this still a binary search tree? It is, because 7 is greater than 5, 7 is greater than 6, 7 is less than 9, right? So it's still a binary search tree. So these are the main steps of our algorithm. This is what we'll have to do. Or step C, if two children, right? So let's jump into Leetcode and let's see how we would code this problem, because it's one thing to understand the problem on the whiteboard, and it's a different thing to code it. And sometimes I found myself like having troubles in coding, actually understanding perfectly how it should work in theory, but like when we're dealing with recursion, having actually troubles in coding. So let's see how we're coding this one. So we know that first thing, if our root, let's say if our root is equal to null, then we don't have a binary search tree, right? So we could just return null, right? And these in Leetcode, it's nice that they give you the constraints, but in the case of an interview, these are your moments where you're kind of like shining, because you could ask these questions and clarify this from the beginning, so you don't wait until the end and then find out that your algorithm is failing, or you have test cases that are failing, right? So now we know, we said that we have to find, we're at step number 1 right here, and we need to find this node, see if this node exists. But for example, in this case, if they're giving us node, remove node 7 right here, would we look even in this tree right here? We would not, right? Because since this is a binary search tree, we know that everything on the left of 5 is smaller. So since we're looking for a 7, which is greater than 5, it doesn't make sense to look on the left. We'll always look on the right only. So we could say something like this. So we could say something like this. If our key is smaller than my root value, then root.left equal delete node on root.left and key. So we're not looking, and we're only looking on half of the tree. Else if, and now is the opposite, right? So if key is greater than my root value, now my root.right is equal to delete node on root.right and key, right? So now these two steps are basically, these two conditions are basically the first step. It's finding the node. And now we're gonna have another condition, else, and in this condition we already found the node. So we already made it to this part right here. We found the node, and now all we have to, we're gonna take it from step A, and we're checking if our node is a leaf. And how are we checking if a node is a leaf? We can check if it doesn't have any children, right? So if root.left is null and root.right is also null, then we could just return null. We could just return null. Then we're making it to step B if it's only one children. So else if root.left is equal to null, then return root.right, and else if root.right is equal to null, return root.left. Good. So now we have another condition. We have another statement. So this portion is step A. These two portions are one children only step B. And now we're at step C. So now we came to this scenario right here. Well, you remember we were showing what happens like if here we'll have an 8 and we want to remove this 8. So we said the first thing, we need a method, or we need a way to find out the maximum of its left subtree, right? So let's go ahead and let's create a small method right here where we're gonna get the maximum of the left subtree. So private tree node find max, and we'll take a tree node root. So we need to find out the maximum, right? So if our root dot right is not equal to null, return find max root dot right. Otherwise, just return root. So this method is going to be called recursively and is going to give us the maximum value of this left subtree, right? So right now we know that we're at number 8 at this node right here, and we're getting the maximum. So let's just create a node which will be equal to the maximum value that we just found. So we're creating a node right here, and we'll call it max, which will be equal to find max of root that left, because we're going in the left subtree only, right? And now what we have to do is we have to replace these values. We found the maximum of 7, and we're going to replace this 8 with the 7, with the value that we just found out. So root that value equal to max that value. And now what we have to do, the next step, is delete this 7, delete this maximum node that we just found out. So root that left is equal delete node on root that left and max value. Here we're passing, instead of key, we're passing this node. We just found out that 7 is our greatest node. We're passing that as a key, so we're going to remove it. And then we're just going to return root, and at the end we're still going to return a root. So I think that would be for this method. Let's give it a try. Let's accept it, and it will be accepted. So again, this is considered, by some people it's considered an easy problem. I personally found it was not that easy, especially this part where we need to think about when it's the case when it's having 2 children, how we're going to remove, and at the same time we still need to preserve the binary search tree, so all the elements will be left of the root will be smaller than the root, and vice versa. So if you have any comments or anything, please consider writing them in the comment section, and let me know if you find anything useful in this video. So also you can give me some feedback so I know what should I change or how should I improve. Thank you, and see you in the next video.